Hello, everybody. Sorry I'm running a bit late here. I had some traffic problems, so that was exciting. Come on, start up properly. Ah, hate when it does this. So this is oh, there it goes. The timeout on the gnome stuff is kind of a pain in the ass. Ah, where are you playing from? There we go. Okay. Okay. Right. So once I get things up and running, if I can get things up and running. Up and running? Okay, I guess we're resetting this. So, just to recap where we are right now, while this is all starting up, I am clearly running about 15 minutes late, so I have prepared absolutely nothing except for what we did last week. And last week what we did was we took a look at a piece of software called pdfcrack. And of course, I have nothing I can show you right now to what it is, but the basics are this is a piece of software that is designed to brute force the encryption on a PDF. The short version is that it basically loads up a PDF. PDFs have certain types of encryption they can have. I think there's 2 or 3 different versions. And this just brute forces the password to decrypt it. Relatively simple, relatively straightforward. It's got a few different features that you can optionally turn on. And in particular, the one that we were looking at was the save state system. So if I'm brute forcing something and there we go. It's taking a long time, rather than having to finish things right now, in a single session, I can break in and basically it intercepts a control C, what is that, sig interrupt? If I had this up already, I would pull up the list and show you. But it handles that, and it will save off to a file the save state, which is the state of the current fuzzing. Or not fuzzing, brute forcing. Sorry, in my head, brute forcing and fuzzing are kind of similar in that both of them are randomly trying things until you get the outcome you want. Clearly, the functionality is different in that brute forcing is trying a known algorithm to do something, whereas fuzzing is basically trying to figure out what that algorithm is without having a human do it. But they're kind of a similar process. So, anyway, that's where we were last week. We took a look at that. We actually ended up finding a couple of bugs in that. And we set up AFL. We ran AFL against this thing for a long time. We used ASAN, the address sanitizer from Clang, to help us catch certain types of bugs. And towards the end of it, we showed that we were getting heap corruption in one of the fields in the save state. So there's a couple things we're going to do here. One of them is, let's take a look real quick here at this. So I was doing everything on this EC2 instance, and I haven't taken a look at it since then. So we are up to almost 500 million test cases. Looks like they haven't found any new crashes, or AFL hasn't found any new crashes, or what it thinks is a new crash, in about 2 days now. But we got almost a full week worth of runtime on a single EC2 instance. I believe this is a medium instance, but I don't remember off the top of my head. So, as far as today's stream goes, there's a few things we're going to do here. The first thing we're going to do is we're going to go through these crashes again, check to see if AFL was able to find anything new. I also want to take a look at the Peruvian rabbit stuff, because one of the issues we ran into, and the reason we didn't land this last week, is that the keep corruption we have is towards the end of all the allocations, and at least at the point that it's making the allocation when we're doing it, there's nothing after it on the heap. So there's not a lot we can do with that. There's nothing there to overwrite, and we can't control the sizes, so we can't do the wraparound thing from the Into the Wilds attack. I think it's called the House of Force is what it's usually called in the old those frack articles, whatever the naming scheme is. So we can't use those attacks either. So we're going to use the Proving Rabbit thing and see if there's anything I'm missing with that crash. So we're going to take that crash, we're going to throw it in there. That's going to be the first thing we do, is get that started and running and give it half hour, 45 minutes to run through and see if it gets anywhere. While that's running, we're going to take a look at the other crashes we have. We're going to do some triaging, see what these 43 crashes look like. And then after that, if the Proving Rabbit comes through and we have something cool, or we have a different crash, we might take a look at that. But failing both of those things, we're going to cheat a little bit. And I wanted to avoid this, but I'm not sure it's going to be possible. Basically, the way we're going to cheat is we're going to mess with the command line arguments a little bit. At this point, I think what we're, like, the realism of this being a exploit that's dangerous at all is going down the tubes. So having control over the command line arguments, I don't think is that much more of a stretch. But basically, by controlling some of the command line arguments, we're going to be able to change the way the heap is laid out and lay it out in a way that's convenient to us to actually get an arbitrary write out of the memory corruption we have. So assuming we have time after all of that, I think once we have a working exploit against pdfcrack, we're going to call it a day. We have thrown tons of fuzz time into this piece of software. There's no real reason to keep looking at this. So the next target for the 0-day streams is going to be Python. So there was a post a couple weeks ago about somebody using memory corruption in NumPy to break out of a Python sandbox. And so I think we're going to, on this stream tonight, if we have time, go through some of the basics for what does that actually look like. So pull down their source code, take a look at it, poke at it a little bit, and just basically get a good idea of what Python memory corruption looks like. The reason we're doing that is because in 2 weeks, the next time we do one of these streams, we're going to be taking a look at starting to build a Python fuzzer. Basically, the plan right now in my head is that we're going to build a generative fuzzer using a grammar for Python and build up a real fuzzer for objects in Python. And hopefully we're able to, so we're going to start with this known exploitable crash that somebody has published. We're going to start with that, and we're going to write a generative fuzzer that can create that, and hopefully a whole bunch of other unknown bugs too. And probably spend a few weeks going through that. That's the plan right now. So let's get started with that. So we have this right here. We were saving these off in O2. So CD O2. And it's just the crashes we're concerned about. So we have all these crashes here. Plenty of crashes. Ooh. And if we remember here, I believe we have the... yeah. So we can take all these crashes and we put together this right here to dump out what they were. So, doop. And we're going to edit this. So, look at all these nice little crashes. Unfortunately, though, it looks like this does not have the... we're not printing out the files always. But, so we want to find the pattern not found right, really. That's interesting. What are we running? So we have pdfcrack. We have ASAN pdfcrack, which I think is the one we want, isn't it? Well, this was giving us ASAN information anyway, wasn't it? Yeah, this looks like the crash we want, right? Let's see here. This frame... Oh, no, that's a read. Really? What's going on here? This seems like crazy talk. We totally had this crash, didn't we? I might have to go back to... last week's stream and take a look at it, because I could have sworn we had found this memory corruption thing. But, where is it? What does this s.sav look like? Yeah, this looks like what we had. So if I do asan pdfcrack ls.sav, right? This gives us a write of this. So what we're going to do here is we're going to take just this crash. What does this look like? So we have not created. So this is the input for it. So we're going to make dir I4. We're going to also make O4. We're then going to copy s.sav into I4. And finally, we're going to, sorry, I'm blanking a little bit here. We've copied that into the input. We want to do AFL fuzz, and we want the -C option, the Peruvian rabbit thing. And so what this is doing, actually, let's get this started and I'll explain what this is doing first. So our input is I4, our output is O4. We want to run O4. We want to run the pdfcrack -L. I believe this is the syntax for it. This should hopefully just work. Whoops, the crash suddenly before. We also needed to do -M 800. Was that working? Yeah, there we go. So now that we have this up and running, so the Peruvian rabbit stuff is basically to do crash exploration. And the idea behind it is that you give it a crashing input. And so let's start off with how AFL normally works. So AFL, when you normally use it, you give it a set of non-crashing inputs, and it basically runs all those inputs through whatever the program is. It tracks taint on that, and basically, I'm not sure if it does taint tracking or not. The short version is you give it an input, and it determines if that input had any effect on the code coverage, if the paths taken in the program. And if it got any new paths, it will save off that input so that it keep doing this and keep iterating through all of its different fuzz mutations to try and get as much code coverage to the program as it can. And then with the idea that that is going to give us more chances for there to be bugs. If we find all the different paths of the program, we would be able to find a whole bunch of different ways that the program interacts with user data. So yeah, that's the basics of it. The problem is that AFL, by default, stops at any crash, and that is a unique output. What the Peruvian rabbit thing is doing is it's basically the same thing, except the input it takes is a known crashing file, and it does not consider any path that is not a crash to be interesting. So basically the idea is that it wants to find all the ways that we can give it an input file that gets through the program and still causes a crash. The idea is basically that if you do that, you should be able to find different ways to excite the same crash, as well as different things you can do on the way to getting there. And the reason that's important for what we're doing right now is because of that situation with the heap. So if we remember what we just said, the situation we're in is that the situation we're in is that we have heap corruption, but we're at the very top of the heap when we get this corruption. So there's nothing after us to overwrite except for the top of heap metadata. And overwriting that doesn't really do us anything useful unless we can make an arbitrarily sized allocation after this. And we can't do that with the way the program is set up. So what I'm hoping for here is that by setting this up and running this through, what we're actually going to end up with are crashes that, due to different code paths taken to get to this crash, will cause the heap to be laid out differently. And hopefully one of these will be laid out in such a way that there will be something after our area of memory that we can actually hit and crash. So that's the theory, at least. Now, while this is running, actually I'm going to take a second and have a bite to eat. I am running quite a bit late, so I have yet to eat my dinner. Luckily, the AFL is going to take plenty of time, so hopefully this is not too boring to watch. What we can see here is that it is in fact finding new unique crashes. Unfortunately, I suspect most of these are the crashes we already know about. Like, there's a whole bunch of null derefs that we can hit. Basically, there are different ways to get the program to skip initializing different variables. And I hope those unique crashes are not that. What I'm hoping for is that those unique crashes are something interesting that result in the same basic crash, but we'll have to open them all up and see. So let's take a look at the other crashes, so the ones we already know about. So these are all the crashes that we got from AFL. What's particularly interesting, so if we take a look at the timestamps here, so we had a whole bunch when we first started this up that all ran through. And it looks like about 2-ish hours into the fuzzing, it found some new path that it was able to generate a whole bunch of new crashes in. And then that ran for a little while. Looks like, what, about 12 hours of that, it found things that AFL thinks are unique crashes. And then for several days, there was nothing. So it's still sitting there, it's still hammering away at the program, it's just not finding anything new. And then finally, it gets a breakthrough here, it gets crash. About 24 hours later, it finds another crash. I guess 18 hours later, it finds another crash. Immediately follows that up with something else that it thinks is unique. And then there's a couple more, again, about the every 18-hour mark. What's interesting about this kind of demonstrates what we expect to see when we're fuzzing, at least a lot of the time. That, it's nice to have you watching. One thing that is worth noting is that these videos almost always get posted to YouTube after the fact. So you can actually use the same URL at any point to watch the recording of the stream. You don't necessarily have to watch it live. It's just that, so Jordan commented in the chat here that he's gonna have to sign off. So all these videos are posted on my YouTube channel after as recordings. So if you miss one or you have to leave or anything like that, feel free to come back later and watch it. They're going to be here probably permanently. At least I don't have any plans to take most of them down. There's a few that I've taken down for different reasons, mostly because I didn't think they were interesting to watch. So there were a couple we had sound issues on, and the content just wasn't all that interesting. So I figured it's better to take those down so you can actually watch an interesting video rather than kind of waste your time on a not as interesting thing that doesn't sound very good. So back to what I was saying. When we were doing fuzzing, kind of what I expect to see is if we have a very fuzzing rich target, see a whole bunch of stuff all at once. And if we're doing good filtering and we're filtering out repeated crashes, then we should see basically like a logarithm. And we're going to try this GIMP stuff, and we can actually draw a picture of it. Oh no, what's going on here? So if we wanted to, we could plot all this out and we should see this. But basically, what I kind of expect to see is that we come in here and we'll have a little bit of startup time. We'll then go way up. We'll find most of our crashes, and that over time, we'll find probably most of them. But it'll never go back down to zero. Like, we'll still get this tail of crashes, crashes, crash, crash, crash. And that's just going to keep on going. And the reason for that is that we can't test all the possibilities. We cannot give the program all... Hello, CFI. Welcome to the stream. Right now we're talking about how, like some of the basic theory behind fuzzing, that I would expect to see a whole bunch of crashes in kind of this middle area where we get most of our test cases in. And then over time, I expect to keep seeing crashes, but at a very low rate. That's actually exactly what we see here. We got a whole bunch of crashes in the first day. The majority of our crashes. So it looks like only 1, 2, 3, 4, 5 out of 42, 43? Out of 43 total crashes. So we had 43 total crashes, and 90% of them were all within the first 9 hours of fuzzing. Everything else was, so the last 5 were then about every 18 hours we'd have another one pop out. And that's basically what I expect to see, that in our first chunk of time to get most of pass covered, and that everything else that we didn't get in that first chunk of time to take a long time to randomly generate an input that gets us there. So let's start with those. We're going to just completely manually triage these things. So let's pull up a nice little other window here. We want to do the ASAN pdfcrack. -L is to load a save state. O2 crashes. And we're going to start with ID 38. So this is the one that is right here. And that is the one that basically 2.5 days into our fuzzing, we finally found this one. And this is interesting. So this is somehow we attempted to free an address which was not mallocked. And this is new. This is not a crash. So everything we found last week, I was aware of ahead of time. I'd gone in the weekend prior, so a week and a half ago. I did some fuzzing. I wanted to make sure that the first target we chose would have potentially exploitable bugs in it. And the way that I did that is I fuzzed it and I poked at it, and I found, look, we have heap corruption in this thing. However, I did not spend 50 some odd hours fuzzing it in order to see what results we got. I spent 2 and a little bit of source code diving. So this result is brand new, and we're going to have to take a look at this one because that's super exciting that this is a completely new crash that I haven't seen before. Let's take a look at the other ones. Hopefully all of these are new and we can actually find one that doesn't require us to cheat, because cheating's kind of lame. I'd rather have a real crash that doesn't require much. So we have address sanitizer segv on an unknown address. PC points to a 0 page. So we have another of these calling an uninitialized pointer. So we don't know that it's an uninitialized pointer. Let's try that and see. So this is in runcrack rev 5. So yeah, this looks like it's probably the same thing. Disassembly flavor int. Actually, before we go too far, I want to .gdb init flavor intel. Hopefully that sticks now. x/I OX805BOAC. Oh, there are 2 slashes there. 1 slash. And I actually don't want this instruction. I want to... So unfortunately, in x86, there's no way to actually know what the immediately prior instruction is. Because instructions are variable size, it could be a 1-byte instruction immediately prior, it could be a 2-byte instruction. So at least as far as I'm aware, our best bet is to do multiple instructions and print it out. However, I'm almost positive that we want something that is 5 bytes prior. And the reason we want it 5 bytes prior is because most calls, potentially all calls, I'm not sure, I'd have to open the Intel manual and figure it out, are going to be a 5-byte instruction. So, yeah, we have a call to set password that ends up resulting in a null. Interesting. So what does save password do? Oh, I want number 3. grep-rn set password. Where are you? So We call set password with the current password. Oh, no, it's using SPW, and yeah, this is the null, like, this is the uninitialized variable that we were aware of. Or if it's not the one that we're aware of, it's the same type of thing, that there is some, like this SPW, so if we do, here, it's in passwords.c, line 39. So this is returning a call to SPW. SPW is this variable right here. And if we search for that, SPW gets set when set wordlist file gets called, or when set charset gets called. So for whatever reason, we bypassed setting those two things prior to actually trying to use them. The problem is that that's not really all that useful. This is a global variable in the BSS, so we can't really do anything with that. It's always going to be zeros, unless somehow you were able to write into the BSS, and if you can do that, you probably already have an arbitrary write or a near arbitrary write, so what are we doing here? So the first crash, super interesting, because that's something new. It's a double free, it looks like, or it's a free of something that wasn't expected to be freed. So, okay. The second one is, let's actually take some notes here. So let's do, and we want to put this into PDF. Notes, pdfcrack.txt. We're going to edit that file. So this one is a free, not triaged. This is the uninit function pointer. So we now want to do ID 40. O2 crashes ID 40. This looks like it's the same thing. I don't know that for sure, but it looks like a pretty safe assumption that especially given the timestamps, that it found one and then immediately the next, like it's a pretty safe assumption that they're probably the same thing. This is the free again, attempting to free on address which was not mallocked. That's interesting. So, address sanitizer attempting to free on address which was not mallocked. However, it has information. Oh, the address is located 0 bytes inside of a 10-byte region that was allocated. What does that mean? So address sanitizer thinks this was, when we went to free this, that it was not mallocked. However, it has information about it being mallocked. That's weird. We're going to take a look at that later. So free, not triaged. So as you can see, I'm not super familiar with actually using address sanitizer. Like, I've used it a couple times, and I know it spits out things, but I don't actually know, like, I've never gone through all of the specifics about how it works. So this is interesting. So, attempting free on address which was not mallocked. The pointer it's trying to free here is F52007F0. And if you look at the previous one, it was F52007DO. And I bet you, if we look at the other one, so pdfcrack, pdfcrack-l, O2 crashes ID 38. Yeah. So these are trying to free the same address, or nearly the same address. Interesting. And all three times, what was the other one? So 41. All three times it is in the free enc data that it does this. And what's interesting here is if we look at this, it's trying to free a pointer that is someplace in libc. Like, it's an offset of libc, right? No, no, it's not. Hmm. Hmm. Interesting. That is very interesting. So we're gonna load up GDB. We won sure dash args bang bang. So if you're not familiar with it, the bang bang here is just it expands out to whatever the previous command was. So GDB dash args is going to take the rest of it as the program to run. And then the bang bang is taking the /pdfcrack -l this stuff as the rest of it. So the full command line that it's running is this right here. GDB-args /pdfcrack -l02 crashes blah. And that just makes it easier to do here. So I can run this. We have our crash here, and play. I'm gonna break on free. So we broke on free. The only reason I'm doing this is because I want to see what the mappings look like. So F5B007D. F5B0. So it was, like, it is a mapped region. It's not completely out of the blue. But those allocations look really weird, right? Like, that's a massive allocation here. Although that might be from just address sanitizer doing that. Okay. Let me think about this for a second. And I'm gonna take another bite while I think. So, if you think about this, I'm not sure if what we're seeing here is kind of an artifact from address sanitizer. The address sanitizer does a whole bunch to back all of the allocations to do its instrumentation. So let's run this again without address sanitizer. And take a look at what this thing is actually doing. So to start with, let's close this. Oh, we have pdfcrack none already. We'll look at that. pdfcrack _ none. And we want to do, where were we? We were in 2? 2. Yes, go ahead and die. So /pdfcrack _ none -l 02 crashes ID 41. So, look at this. So this very clearly looks like we are getting a kind of heap corruption I was hoping we would get, in that it thinks the next pointer, whatever the in a free block, is no. So the size of the block right now is that right here, and this is a heap pointer. So for whatever reason, this causes the size of a block we're trying to free to be a heap pointer, which is clearly wrong. Like, this clearly is because of heap corruption. Interesting. How about some of these other ones? We had this one, which Asan thought was, for whatever reason, already allocated. So that was 40. We also want to look at 38. So 38, assertion. So this is another malloc assertion. So there's several different assertions that malloc makes to try and stop exploiting heap corruption. I'm not going to go into all of them right now, but the short version is that it does a number of different checks to try and make sure that when you're freeing or mallocing pointers, that it at least looks sane, that the metadata is at least within a sane range, that it looks kind of like what it's expecting to see. So that's what that is. The other one is a assert. They're basically the same thing, except for how they're handled. This is a this assertion I haven't really seen much of. This format I'm pretty familiar with. Like, when you get like heap corruption, you see these all the time. This is just DL malloc has some basic checks in there, and this is not right. So we did that one. And we also want to take a look at, so we had 38, we had 40, or I'm sorry, we had 41, and we want to look at 42. Okay, so 38 and 42 are resulting in the same thing, where 41 gives us the crazy town. Right? Okay. So, ooh, look at that. We're getting more unique crashes. So for the people that joined us a little ways into here, what we're currently doing is we're running pdfcrack with the Peruvian Rabbit in one of my screen tabs to try and find pathways to the heap corruption we knew about. So last week we found some heap corruption, which is just a out of bound, what do they call it? The linear out of bounds write is the new term for it, where it just, I think, stir copies, or it uses scanf for a string and dumps it onto the heap for as much data as we can give it. So we've had that for a while. We found that last week. However, trying to land that wasn't going to be feasible. So we're using pdfcrack to try and find other pathways for that which might be easier to land. While we're doing that, we're looking at some of the other crashes, and we're going to try and figure out how to land those. And this one in particular looks pretty promising. So let's take a look at this. So we want to look at, let's start with the format for these are relatively human readable. So ID was 38, right? 41. 41 is interesting. So what does this look like? What? Okay. What? So clearly, we have some corruption here. So the way that this format usually looks is we have a word list, and then parentheses, the length of the word list. And then a space, and then the file it's going to try and load. What on? No. Yes, that is how that works. That's how word list works. What is going on? Okay. So this is the heap corruption we knew about and we were looking at. Comparing these two real quick, we have PDF 1.4. The revision and version are different, but I don't think that matters that much. I don't know what that means. The metadata looks the same. File ID are the same. Filter is a different number, but it looks similar. Like that looks relatively similar. The O is the hash for the owner password. The U is the hash for the user password. User is 9 or 1. I don't know what those are. Permutate. Okay, those don't look like they matter too much. What's really interesting is in this freed one, word list is getting, like, I don't know how that's getting parsed. That's interesting. So what does that actually look like? Oh no, what have I done? I thought I fixed this. Why are we going so slow? Okay, yeah, here we go. Oh, I had caps lock on, didn't I? No, what are we doing? Let me input. Why, thank you, AdChan. I enjoy doing these. They're a lot of fun to do. I started doing these streams about a month and a half, 2 months ago, and I find they actually really help to just sit here and talk through things in my head as I'm working on stuff. So I would like to see more people do streams like this, especially for things that I'm not as familiar with. Like, I would really love to see somebody take a whole bunch of like web challenges or crypto challenges and do exactly what I've been doing with these. Walk me through how to solve crypto challenges or how to solve some of these web challenges and things like that. I would definitely like to watch that because that's a skill set that I can sometimes stumble through, but I'm not great at. And having somebody who actually is good at that, I would love to watch that. So if you know somebody like that, you should try and talk them into streaming it. So, where are we? What are we doing here? Come on. We are typing correctly. This is the downside to this interface that I use. So I use Screen and Vim is the set of windowing stuff that I use, which works great. So I SSH into the EC2 box we've been using for this. I can do Screen-R, and it just works. The problem is that Screen and Vim kind of conflict a little bit sometimes with how they capture certain keys. So sometimes everything breaks. So, where were we? So we have this input, and this is what the normal crash looks like. And this is what that free crash looked like. So this is the one that causes a free in ways that I don't understand. So let's go take a look at it. So GDB, I want to do pdfcrack. Let's use the none variant. I don't necessarily asyn might be manipulating things, and I'd rather take a look at it without that. And we want, so unfortunately, current versions of Ubuntu do context-aware tab completion, which is really great if I'm doing something it understands, but it breaks completely when it doesn't understand it. So what I'm doing here is I'm running it first, and then I'm going to, so Adchan is saying I should try tmux. I've thought about switching to tmux. Basically, the thing that's preventing me from switching to tmux is that there's a couple things that I use on a somewhat regular basis that already have Screen installed but don't have tmux. So speaking of which, I can't use that argument here. At least at one point, Screen was installed by default on one of the servers I was using every day, and tmux wasn't. So I got really used to using Screen for everything. For literally no other reason than that is why I use Screen. Because personally, I'm a little adverse. I don't want to install software that I don't need to, unless it's a clear problem. So, it's that crotchety old man argument. Use the things I'm used to, and I don't like change. Change is bad. But I can put up with a little bit of annoyance to not have to learn something new. So, as long as it doesn't absolutely kill me. Byobu. I don't know what Byobu is. So, Josh mentioned in the chat that Byobu, Byobu. I've actually never heard of that. I don't know what it is. What is it? Let's go take a look here. Byobu. Byobu. Byobu is a GPL3 open source text-based window manager, and interesting. Originally designed to prevent elegant enhancements to otherwise functional Screen for Ubuntu server distribution. Interesting. Huh. That is interesting. So does this have most of the same key bindings and stuff? Yeah, I might have to take a look at this. If assuming it's pretty close in line with Screen, then all the muscle memory is already there. Interesting. Thank you very much. I'll have to take a look at that. So, where were we? We were taking a look at this crash. In particular, I want to see what's happening when they actually parse the word list. So let's start with main.c, and they call, where is this? The init pdfcrack. Before they do that, we load up a word list. Where are we here? So up here a little ways, we should see, yes, we have a recovery file. We want to load the state. So load state. Load state runs through this. At the end of load state, we have a call to pw load state. So this is where it loads some of the stuff. And in particular, I expect to see in here, like, this fscanf should be returning false, and if this returns false, we bail all the way out. So what's happening here? Actually, before I take a look at that, let's do a xxd of this thing and see if maybe there's some wackiness in the way Vim is displaying that to me. No, that totally looks like a bunch of non-printable characters. Word list 4D. So this is a 4. This is a lowercase d, and then a null byte. Why is that? Okay, we're going to take a look at this. So we're in here. I want to break on pw load state. Yep, run it again. So we're here in pw load state. Let's display /I believe EIP, right? We had to compile it as the 32-bit version for using ASAN because it plays better with AFL. If you're going to use ASAN, I have not verified in this information, but the instructions say if you use ASAN, compile 32-bit on a 64-bit system because it helps with the memory stuff. I just do what it says. So we're now in this function. Let's step. So we are now doing the PW. We're still in the initializing. Step. So we're still. We're still in the function prologue. So function prologue. If fscanf file string string underscore PM. So we're right here. Basically, we're making sure that we load this right here. So step. It's pushing arguments. We're going to make our call to fscanf, call fin. So we just returned back from that, and we returned 1. So yes, we did return one thing. So we're going to continue here, jump if it's 0 or negative, because JLE, so it does test EAX, and then a JLE. So that's going to check to see if it's 0 or less than 0, I think. Pretty sure that's how that works. I actually don't know how that works with when you test the same thing. I'd have to walk through it, but it doesn't matter too much. So we're going to check to see if it's generative. Else, if it's a word list, it is a word list. So if fscanf file word list %d. Gotcha. We're going to step into this. We're pushing arguments. We call it fin. And what does EAX look like? EAX is 1. How is that 1? So this is word list open paren for D. And somehow fscanf word list %d decoded that. How did that happen? I don't understand. Like, it has to have that close paren, doesn't it? And that close paren isn't there at all. Like, it's not like it's not like there's some weird stuff in between it. It's just not there at all. That is weird. What? Okay. Well, let's step a little bit more here. So we keep stepping. We see that worked fine. We're at line 349. So set new. Oh, wait, no, what? No, we're not at line. We're line 222. So yeah, we're at the string malloc here. Sorry, I was looking at the byte offset to the function, not the line offset like I thought I was. So let's keep stepping here. So you're about to push EAX. Oh, so it's going to keep. I did not realize that scanf worked that way. So what it's doing is it read and like it kept trying to decode stuff until it failed. So it decoded word list open paren. It decoded a number, which was 4, and then it failed to keep going. So it returned that 4 that it got into len, and it was able to decode 1 parameter. Interesting. That's really interesting. Okay, so we did that. We are mallocing space. So we call malloc. Let's return from that. We malloced 4 bytes. I assume that worked fine, right? Yeah, that worked fine. Let's step some more. We're finishing up that call. We're now going to do an fscanf of the file, looking for that regex. Okay. So let's fin. Awesome. So what did we get as a return? It was able to decode something. So what does this actually look like? I don't actually know what this is. Okay, so let's walk through what this is doing. So the search it's doing is percent square brace caret new line square brace new line. So if I understand what that's doing, it is trying to eat everything that is not a new line until the next new line. At least that's the way that I understand that thing working. Okay. We were able to decode one of those successfully. So what is... Let's print out bytes. What exactly is string? You know what string is? You do know what string is. So we got the 6.4. So we got 6.4, null byte, 20.6.4. We got all the way... So we decoded all of that. We decoded the rest of the file. Okay. And then we're going to null terminate at length. So we're going to null terminate here. Okay. Step. Step. We null terminated it. And everything is fine. Huh. So we return all the way back here. We're now in load state. We keep going, keep going. We're back in main. Interesting. We're back another step from here. Huh. So we're calling loaded state now because apparently we're not quiet. We push all these arguments in. Wait. What? Where are we? We are in... We're at line... How do we end up at line 104? What? Okay, so according to this... Oh, no. We are still in... Okay. Two, 6, 9. No! Go to line 269. Okay. We are in this buffer, line 269. There we go. We did that printf, it worked, and something was confusing. We are now closing this file. That looks fine. Fin. Let's keep stepping. We did that successfully. We're on 273. We check to make sure that there's stuff to crack. If there's a word list file, which we did give it a word list file, it is now going to try and fopen that. It's calling fopen. This what? Really? That's returning something? Oh, I apparently have a file called D. Okay. That's interesting that it was able to actually find a word list. Huh. That is entirely unintentional. That's really interesting, though. Okay. So we have that. It succeeded. Let's go until we get a free. Okay. I keep forgetting. I'm so used to looking at 64-bit stuff that the R is just a complete habit. 804 EED. That's not what I wanted. That's what I wanted, I think. That's clearly not right. Right? That's the argument. Now, how does this work on... Okay, let's walk through this. When we make a call on 32-bit process, we push the argument, and then we make a call. What a call does is it pushes the return address, and then it jumps to what we called. So what we should see here is you should see the return address, and then what we called it with. So we're actually trying to free... Oh, that is valid. Oh, right, because we're running it in GDB. Duh. So what I was thinking here is that 805 should be the first 4 bytes of something in like the data section of the BSS or something. Which, if that is being passed to free, is clearly wrong, and we must have screwed something up big time. However, because we started the process in GDB, GDB has some internal stuff. It changes the way malloc handles returning addresses. And the heap is going to be right up against that writable section for the binary. So this is not what I thought it was there. It is just that we're trying to free a valid pointer here, right? So if we do x... Oh, come on. Don't do... Oh, there we go. 20x... OX 80581E8. And that looks perfectly valid to me, right? And we want to subtract 8 bytes. So we want to look at the header. So this, for whatever reason, we allocated 59 hex bytes to this thing. I think this looks more or less valid. So 59 would be 58 bytes that are allocated, and the previous is in use. So 10, 20, 30, 40, 50, plus 8 bytes. This is junk. Because this is in use, that's part of our area. Yeah, that looks perfectly reasonable. So we should be able to fin from this, fin from this. That works fine. So we're in the cleanup right now. 2x $ESP 805.912. Okay, 805.9218. Not what I said. This is what I wanted. So this time we're doing 37 bytes. Oh, I'm sorry, we're doing 39 bytes. So 1, 2, 3. Again, that looks pretty reasonable. The next thing is 39 bytes. That seems like we've not hit whatever the corruption is. Fin. Continue. We're freeing some more. 9250. That's the other thing. Don't care about this. 91FO. This is probably the same thing. So what I'm doing here is I'm just continuing because those pointers were basically all in a row, which means they're probably all the same, whatever that 38 byte thing was. Probably just more objects of the same type. This, however, is backwards, so this might be interesting. x/20 wide x 80581bo minus 8. This is another of these same objects, not interesting. But there is a really big allocation right after it, which is a little bit interesting. Not super interesting, but a little bit interesting. Let's dump this. 96AO. 96AO minus 8. Ooh. So this is one of those big allocations that has basically nothing in it. It's A and then a new... Oh, this is the word list file we gave it, right? Yeah, this is the word list file we gave it. Okay. Huh. So when it opened the word list file, it had memory corruption. So somehow the object for the word list file has memory corruption related to it. So that's interesting. So somehow we're getting... Let's go back and take a look at what we're doing here. So we did the load state. This worked fine. Oh, no, that's not what I wanted to do at all. If recovery, we free the word list file, then we load state, then we come in here. If word list file, we're going to fopen it and do stuff with it. And then I assume at some point we're going to take the word list and we're actually going to read all that stuff out of it. Where does that get used? Oh, no, stop that. 4 is what I want. Grep word list. Okay, so the word list, that's convenient. They added support for word lists and PDFs greater than 2 gigabytes. Huh. Add support for different new line stuff in word lists. Okay. So sometime after we allocated this thing, we end up, but after we have our heap corruption is when the word list gets created. And when we free the word list is where we're failing one of the checks. So we've somehow manipulated something around it in such a way that glibc thinks that the allocation is wrong. But I'm not sure what that does for us, right? So we're still looking at the same bug. It's just we have an allocation that is a little more controllable than I thought it was. So the word list file, the word list is only looking at this grep list. Everything up to, so everything between this and 277, these are all stuff we've already looked at. When we call init pdfcrack, we're passing the word list file, and if it's let's go take a look at this. Okay, so line 300, right here. So we're passing word list, and if word list file will pass word list, otherwise we'll pass generative. With capital word list. Oh, we're passing which mode we're fuzzing in. Okay. And then word list again. Okay, that's a thing. And then it gets freed as part of the cleanup. Okay. In particular, it's freeing both word list and word list file if word list is set. These seem like at least somewhat reasonable things to do. One of the problems here, though, is that we're still in a similar situation that if we can do something at the free, there's nothing happening after that free. So we might be out of luck anyway. But, so we have the method, and then we have file. Where does file get used? We have file, file ID, file len, neither of which we care about. Init passwords. Okay. Init passwords gets passed in file. I believe we're word list, so we're going to set word list. Word list is equal to file. Why didn't, oh, because capitalization changed. Of course it did. Why would you use consistent capitalization throughout an entire program? That's just crazy talk, isn't it? So word list is the file object. Word list name is the other thing. So we do word list set password here. I don't know how we filled that thing with data. Okay, you know what? Where were we? So this is where we were. Does this work? Fortunately. Fortunately, this does not tell me what I was hoping it would. Well, I can do this, right? So this -5, is this called? Oh. Oh, we are closing an F. Oh. This is not what I thought it was at all. Okay. Wow, I was completely going down the wrong track because I didn't read this properly. So we're in pdfcrack, and we're actually crashing this time in fclose, not in the thing that has it. So it looks like fclose has set b, which is probably setting up a buffer. Okay, so going all the way back here, if word list file, we're going to fopen it. So fopen is going to return stuff, and that is going to be the next allocation after our thing. Okay. Interesting. So this is probably the same corruption that we've seen before, right? In that we're still just we're just creating an object after it that happens to be set up in such a way that we can get all the way to the free. But I don't think it's all that interesting, right? Because basically what this is complaining about here is that the what's the word I'm looking for? That the so we've modified the top of the heap, the size of that, to be some random value. So when we're crashing here, so let's set this all up, right? So we're going to break on OX 8049060. we want a pointer, not a piece of crap. We want to break there. Start this D free. We don't. What? IB. Oh, right. We want to delete 2. Continue. Okay, so we're at the F close here. Now I want to break on a free. Continue to free 2 WX dereference ESP. That looks like the address I was expecting to see, 80596AO. That looks like exactly what I was expecting to see. Okay, so we allocated this thing. Oh, and we want wide X's, not giant X's. What is that plus 1,000? Yeah, so this is what I was kind of expecting to see, right? So the way the heap works is, so this is the pointer right here that was passed to free. The 8 bytes, or 16 bytes on a 64 bits binary, are the metadata. This is the important part. So this is saying that the size that is currently allocated is 1008 hex bytes, and that the previous block, whatever comes before this on the heap, is currently in use. Because that low bit is set, it means that the previous thing is in use. So we jumped ahead. So if we jump ahead from this, we want 1008 hex bytes. So 1008 hex bytes would be the start of the next chunk. And so what we're getting a complaint from is it checks to see the size of this is valid. And this clearly is not a valid size for the top of the heap. In fact, this is almost certainly just the value we wrote onto the top of this heap. So, not really useful at all. But why did ASAN tell us that we were freeing something that wasn't right? That's interesting. I'm not sure why ASAN was telling us that. Because this does not look particularly manipulatable. Manipulable? This does not look like something we can really do that much with. Because we're kind of stuck. Ew. Okay, well, at this point, we spent another hour taking a look at this. As far as I can tell, the crash is the same thing. Like, we didn't really get anything super interesting out of this. So, let's do this. So we've been running the Peruvian rabbit stuff through pdfcrack for about an hour now. So let's take a look at what the results it has are. So these are all in 04/crash. We want to find the files in there, and we want to execute /asan pdfcrack -l, and I want to pass in the file. Then we're going to be done with it, and then I want to do all of this into triage. Let's take a look at triage. So what we just did here is we took all the crashes one at a time. We ran them through the ASAN binary. And what this should do is this should tell us what exactly it is that ASAN thought, right? So all of these should be crashes, and they should look pretty similar. The first one is a stack buffer overflow that we still haven't really looked that much in detail at, but that I don't think is particularly useful. It's a 1 byte out of bounds read, which I believe is getting passed into an MD5, so I don't really care about it. We then have a whole bunch of these, which are that uninitialized function pointer. What is this one? So this is one of the asserts. We don't really care about that. We have an uninitialized function pointer. Keep buffer overflow, right of size 5. This is the one that we're aware of. This is writing out of bounds using fscanf. So this is the one that we are quite aware of. ASAN is complaining about. Uninitialized function pointer, uninitialized function pointer, uninitialized function pointer. So we didn't actually get anywhere new, really, which is sad, right? So this looks like it's all basically the same crap we've had. Let's run it with the none. So we want the pdfcrack none version. What does that look like? Nothing, 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 nothing. Failed assert, nothing, nothing, nothing. Well, that's disappointing. So it looks like none of these are super useful. What I was hoping for is that if we kept doing this and we would hopefully get something out of all of this, that would result in something that looked relatively exploitable. Now, it's entirely possible that given, large sums of time, we'd be able to find a way to actually exploit this. Like, this is still clearly heap corruption, and I am not willing to discount any sort of memory corruption as being non-exploitable. I have seen way too many bugs that I looked at and I said, no, there's no way you're going to do anything useful with that. And then have somebody turn around and be like, code execution, we're done here. Well, very rarely was it that fast. Usually it is they bash their head against it for days or weeks or months, and then they come back and like, ta-da, look. So it's entirely possible that without cheating, we can do the same thing here and get something useful. However, that isn't that interesting to me. Like, the whole situation that I can somehow supply you with a pdfcrack save state, get you to load it and use it, this is not a very security relevant bug to begin with. So let's just land it and move on. Let's look at something more interesting. So let's do this real quick. So if we go back to our source code, where were we? We come back in here. We noticed that the, which of these is it? The input file. If we supply multiple input files, if input file is set, we'll free it, and we'll stir dupe a new one, which is awesome. It does the same thing. Oh, no, it doesn't. No, it doesn't. It does the same thing with word list file. No, it doesn't. Huh. For some reason, I thought the word list file acted the same. Basically, we can, if we supply the -l argument twice, the first time through, it's going to set it, it's going to stir dupe it, it's going to set it. The next time through, it's going to free it, it's going to free what was there before, and then we're going to stir dupe the new one. And so, the reason why this matters is stir dupe is going to call malloc underneath the hood, so we can get that to do something useful for us. And if we take a look at what's going on further down here, so we finished doing the argument parsing. It sets some defaults. It potentially dies for a couple different reasons. And then the very next thing it does is it calls calloc. So if we can get this set up properly, then what we should be able to do is get a hole in the heap that is just the right size, such that nothing will get put into it, and the very next thing after it is this call is the E, which is a fairly complex structure, right? So if we take a look at this thing, of course, it's the single character variables are not so easy to search for. Main, yeah, we'll just take a look at it anyway. Where are we? So an enc data is this thing. So an enc data has several pointers. Looks like several buffer pointers of different types. It has booleans, it has integers, it has lengths, and it has tons of stuff in it. So if we tweak this and we create a specific command line argument that works, well, then we can actually get something out of this. So the disappointing part about this is that this is kind of stretching the plausibility of this being an exploit that would ever work against a person. Like, the only way I can see this ever actually, like, owning somebody's computer is if, you go on some random forum and it says, oh, hey, I'm trying to crack this PDF thing. Here's the command line I'm trying, and here's the save state that I'm trying to use. Can anybody else take a look at it? And then maybe you get somebody who tried and pulled it down, and like, this just seems implausible as a real attack vector. But it's good to show some of the basics of trying to land some of this stuff. So, let's start with this. So the first thing we want to do is we want to run. So we have, where is it? Let's come over here. So we have pdfcrack none -l, and we want to use s.sav. Just because this is the one that is relatively straightforward. And we're going to load up GDB. Basically what we're going to do here is we're going to instrument all of the mallocs. So I want to break on main, run. I want to break on malloc now. So the reason we didn't do this prior to main, so if we break on malloc prior to main, it's going to include all the mallocs for setting up the process. And that's quite a few that we would just have to filter out later. Whereas doing it this way, I know that all the mallocs after this are the ones done by the program. So we did a break malloc. I want to do commands. I want to do silent, x/x $, ESP +4. And I want it to be a wide byte. So we want to print out what that argument was. That's it. We then want to continue. I'm going to end this command. So what we just did here is we basically set up a very primitive tracker for malloc. So when we run this, it's going to print out what each of those arguments are. And finally, we want to set logging on. So now all the stuff GDB prints out, it will also save off to gdb.txt. Now we continue. It runs through here. It prints stuff out. It dumps it out. So if we come in here, we should be able to see gdb.txt. We have, oh no, what is all this? Oh, there was already one there. Okay. This is what the relevant stuff is. So that is a list of all of the allocations that the program made after main started. So it allocates 6 bytes, 6 bytes, 158 bytes, 1000 hex bytes, 10 bytes, 9 bytes, 20, 22, 400, 158, 54, 10, 1000, 1919 1C. So, one of the big problems here that probably is going to come up, and that I don't know off the top of my head how this works, is how exactly, so when you make a big allocation, you can trigger a consolidation of the heap. And basically what that's going to do is that's going to go through all of the current allocations. It's going to dump them out. One of the things that it can do is it can dump things out of the fast bins, which is the area that this is going to be easiest for us to do it in. But let's give this a try anyway. So what we want to do here is we want the first -L. Let's make it, so if we make the first -L, sorry, I'm trying to think through this. You know what? Let's do this again. So we want to edit s.sav. Instead of mallocing 1, so it malloced 1, which is this one right here. And basically what this means is that, yeah. So I think if we give it a -L of 1 byte, it should malloc it, and then free it if we gave it a second -L. Right? That's how that should work. Because one of those 6s should be that stir dupe. right? So if we do this, what I expect to see is if we do -ls.sav-la, we do this. Still get the same thing. We do not get the same thing, do we? I mean, no, it's about the same thing. Yeah, it's the same thing, more or less. Just ASLR moving around on us. But we do gdb-args bang bang. We're going to break on, oops. Where is this thing? We want to break on the free. I want to break on the free. I'm trying to think here. Where do we want to break? Let's break on that PW. So PW load state. Continue or run. They're broken here. Step. So we're going to keep going until we hit that fin. Step. Basically what we're doing here is we want to step until we get to that malloc so that we can take a look at what that malloc returned. Step. So now we're about to hit this malloc. So we are now in the malloc. Return. What did we get? So we got 5099230. So, what is that? Ah, that's unfortunate. Huh. So as we can see here, -8. What we ended up getting, right, because it's going to round. Is it going to round up that much? So when you call malloc, it does not just trust the size that you gave it. It rounds up to the nearest round number, which is 8 bytes on 32-bit and 16 bytes on 64-bit. So when we requested to malloc 1 byte, 2 bytes, something like that, instead of mallocing what we gave it, it malloced enough space for that, plus the metadata, and to align everything. But that did not give us the bucket that we had expected from the -L, which is odd. Let's restart this again. Break on main. Restart this again. Break on malloc. We'll do the exact same thing we did before. Commands, silent. We want to do x/wx $ESP plus 4. Continue, end. And we want to set logging on. Continue. So we malloc 2. We malloc 2 again. And then we freezed. What is going on? Oh, and then we got to where we were. Unfortunately, the hole we're making, it seems, is not working out the way that I'd hoped it would. One of the problems here is that if we pick something that is bigger, that would have enough space for it, then... Oh, that's what's happening. Duh. Right? So we malloc 2, we loop back around, we free 2, and then we malloc 6. Those are effectively the same size. What we need to do is we need to change the input file we're giving it to be bigger so that it can't use that buffer. Duh, why didn't I think of that? So move, we want to copy s.sav to many s's.sav. So now if we come back in here, we want to do this one. gdb-args bang bang. We now want to break on PW. Oh, hone? No. Load state. Run it. Step. fin, step, 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 step. Step, 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 step. Fin, fin, step, 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 step. Malik. Fin. Okay. No, it did it again. That's not what I wanted at all. Aroo. Okay. Restart. Yep. Break on main. I want to break on free. And I want you to do the same thing we were doing. So silent x/x $ESP plus 4. Continue, end. Continue. So those are all the pointers we freed prior to hitting this crash. So I expect that this one, so this is the one that we died on, and I expect that this one should be that first one. How did it get consolidated like that? So, like, that is not what I expect to see at all. Because we malloc 2. We did that stir dupe. Then we freed it. So, this is unfortunate. So for whatever reason, what we're trying to do here is basically arrange the heap in such a way that we have an opening that we can smash other things from when we finally get our heap overflow. And it isn't cooperating with us the way that I would like it to. One of the problems here is that if we use a bigger size for that first -L, it's not going to matter. Because I believe that the fast bins are, if they can't fill something, will break apart a larger fast bin. Which means it's going to get returned to something else anyway, which is not what we want at all. Actually, this one is earlier. Maybe, are you it? No, I want this thing. You're even farther off. Right? Like, you're a big allocation. You're 18 hex bytes. That's pretty big. Huh. Okay, you know what? We're going to come back in here. So we should have gotten into this right here. Be main.c line 141. Run it again. Continue. Okay. x/5i EIP. We're going to push EAX. So EAX is currently that single A. And 805.8008 is the pointer. Okay. So step, 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 finish. We've now... What? No. What? Why did you return there? Oh, because our command is still in there. So we still hit the breakpoint, so it's still... Duh. It continued, and this is where we are now. So if I do 20x at 0x805.8008, it's already refilled it with something. What did you fill it with? How did that happen? Oh. Okay. So, what we're seeing here is that because it was the top of the heap when we did this, when we freed it, it just got consolidated back in and used just fine. So what we actually need to do here is we need to have a dash L of 1 byte, then some other argument that does a stir dupe. Then we can have something that we want. So, oh, nope, that's not what I wanted. That's not what I want. Quit. Okay. So pdfcrack no dash L and A. Let's do dash C, something big. Dash L again. This time, this thing, like that. Okay. GDB. Oh. Yeah, let's just do this. Let's see if we can get lucky. Run. Oh, right. No, I wanted that breakpoint, didn't I? And that is PW. So break PW load state. Restart. Yes. Step. Actually, you know what? I really need to learn what this line is, and we're just going to break on that instead of doing all this stepping next time. Okay, so we have a malloc here. What does malloc return? Malloc returned this thing. And you're at the top of the heap still. Damn it. Why do you hate me? Why, oh why do you hate me? Okay. Show args. So I want to set args dash L A dash C many A's dash L this thing. So this, let's do this. So we get this far, continue. We have this right here. Step into the free. Fin. Ah, it still caused that breakpoint. That is awful. Eight. What did we get in there? We still end up with that same. No. Ooh, this might not be possible. That's unfortunate. Right? So if we take a look at this. No, I mean it. So we're at this free. EX minus 8. Oh, so it rounds up to 16. Bleg. No. Round it up to the nearest 8 bytes. That's what I would expect it to do. Because it's 8 bytes for the metadata, 8 bytes for the stuff we put in it. And the next thing is 8 bytes, right? Because this is what we put in it. That is 8 bytes exactly. Well, damn it. So what's our next option? Our next option, well, so we have a couple of options here. One is we can make this big. If we make it big enough, then it is going to get kept, I think. So at this point, we've been looking at this for about an hour and a half now. And I think at this point, probably going to call it a night. Because we're going to spend probably another 20 minutes to half hour poking at these arguments to get the proper heap layout that we want. And after that, it's going to turn into using that to get an arbitrary right into someplace useful. Like my plan here for exploitation is I'm going to manipulate these command line arguments to get something. Like basically get the layout such that E will get allocated immediately after a open chunk of memory that then gets filled by the overflowed buffer. We can use that to get an arbitrary right, because one of the fields in E gets written with data that we supply. So, that's unfortunate. It's unfortunate we weren't able to get any farther. And it's also unfortunate that it doesn't look like there were any other bugs that we managed to find, or any other interesting crashes, because it looks like all the other crashes that we got were still this same heap overflow. They were just crashing in slightly different ways. Wait a minute. You know, I said that, but it's really interesting that ASAN didn't catch the out of bounds right. That might actually be more interesting than any of this. That when we do the ASAN pdfcrack with -L O2 crashes ID 38, we got all the way to the free here. And ASAN was fine with that. I'm much less convinced right now that this is the same thing. Yes, it exhibits the same crash. However, if this was identical, I would expect to see ASAN yelling at me much earlier on. Because how does this happen? How does this happen? Free enc data. So ew. This one's oh right, this is the other one. So like all of these bytes should have been an out of bounds right that ASAN should have caught. Why didn't ASAN catch these? Huh. I have no idea why that. Like, I would entirely expect ASAN to catch this, but it's not. Instead, it's catching when we go to free it, which, I mean, I guess is close enough, right? Like, it's still catching. It's still catching stuff, just not catching the right thing. Like, it didn't catch the out of bounds right, it's catching a free later on. That is odd. And I don't have a good explanation for why that's happening. But anyway, so what I was saying was that at this point, probably going to call it a evening. We've spent 2 weeks on this now. We have heap corruption in this thing. At this point, I'm not entirely sold on continuing this. Like, it'd be nice to finish this and have a working exploit. I'd also kind of like to go on and go look at Python instead. So after this video is done, I think I'm going to go on Twitter and post a poll on what people think what would people most like to see. Would they like to see me try and finish landing this? In which case, in 2 weeks when I get back from vacation, we will work on landing this and probably do some research between now and then and figure out exactly what's going on here, so we don't spend quite as much time going around in circles on the stream. And hopefully, in 2 weeks, then we would be able to do what I planned for today, which is spend maybe an hour on this and be done with it. Or, if people would prefer, we can say, well, we found this 0-day in pdfcrack. We can show that it's probably exploitable under some pretty absurd conditions that aren't entirely realistic, but might come up. So we could start off next week, or in 2 weeks, looking at Python stuff. Start by looking at some existing memory corruption vulnerabilities probably start with NumPy, what those look like, how we might excite them, and then start writing a test harness and fuzzer for those NumPy objects. But figure while I am putting stuff on the screen for people to watch, it is kind of up to the audience about what they would most find interesting. Like I'd rather do whichever of those two things that the audience thinks is more interesting, because I mean they're both interesting to me. I'm just getting pdfcrack is getting a little bit old because this is now my 3rd week looking at it. So getting off it would be kind of nice. Then again, landing it and being done with it would also be very nice. So yeah, if you don't already follow me on Twitter, it is @MurmusCTF. You should follow me. I try and tweet out whatever the topics of the stream are going to be, as well as I have YouTube set up to automatically tweet out when the stream starts. And I also, when I'm late like I was today, I always try and tweet out that I'm going to be late and a rough estimate of how long it'll be. So you should follow me on Twitter if you are not already. And I'll try and put up a poll there to see what people would like to actually watch as far as what to do in 2 weeks. Other than that, the big thing is that next week I will not be streaming. I'll be on vacation and completely away from the internet all week, so there will be no streaming going on for me. If you are interested in watching some offensive security streaming, instead, you should go watch Ginvale's stream. I believe next Wednesday he is looking at some kernel exploitation on Linux, and should be a lot of fun. It starts approximately 5 hours before this stream does, and usually goes for an hour or two. It's 8 p.m. his time, which is 2 p.m. Eastern. But if you're looking for streams to watch while I'm gone, or while I'm here, Ginvale's is amazing, and you should go watch that. Other than that, like always, if you have questions or comments, please let me know. Either leave a comment on the video or send me a message on Twitter are probably the 2 easiest ways to get a hold of me. However, Slack and RSC are also both options. So thanks everybody for tuning in. Thanks for being patient while I was late, and I will see everybody in 2 weeks. So bye.